Hello everyone, and we're talking about the science of c today. And c, as you may know, is the speed of light. And so we're talking about how we started to think about the speed of light and how we have attempted to define it over the years. Let me just point out, for the sake of accuracy, in the title there, c is a capital C. This is not the scientific symbol. If you're using c in equations, you always use a lowercase c. So that's important. Don't want to mislead anyone here. So by way of an introduction, let's just think about how we thought about light. For many years, people thought that light was infinitely fast, that it propagated, which just means traveled, instantly through the ether. And the ether was a substance that filled empty space. It's like a universal frame of reference, really. The ether was stationary, and everything else moved through the ether when it moved through space. And many great minds of their time supported this wrong idea, including Aristotle and Descartes. And Descartes in particular, many of his ideas are still used today, but not the ether theory. Then came Galileo in the 17th century, who was one of the first, although not the very first, to question this idea that the speed of light was really infinite. So, that's what he asked. Is the speed of light infinite? Galileo states the following, and these are his words, so they're a little bit archaic. Everyday experience shows that the propagation of light is instantaneous, for when we see a piece of artillery fired at great distance, the flash reaches our eyes without lapse of time, but the sound reaches the ear only after a noticeable interval. And a piece of artillery is a large gun or a cannon or something. And in a later work, Galileo suggested that maybe it would be possible to devise a scientific experiment to measure the speed of light over a number of miles using lanterns and telescopes. And this might be able to prove or disprove the speed of light, whether it was infinite or not. So somebody actually tried this, not Galileo himself, but the lantern experiment was attempted in 1667, and this is how it went. So you had two people on two hilltops, approximately 1 mile apart. So on hilltop A, there was a person who would uncover their lantern, and then as soon as they saw the light, person B, as soon as they saw the light from that lantern, the other person on hilltop B would uncover their lantern. Person A would then record the time between opening the lantern until they saw the light of lantern B. And so light would travel from person A to person B, and then the light from person B's lantern would travel back to person A. So we're measuring the speed of light over 2 miles, there and back. And with that in mind, we can apply a simple distance over time equation. So the distance is 1 mile between the hilltops, so the speed of light would be 2d divided by the time it took for the light to return. This experiment was partially successful. The people who took the data were able to suggest that the speed of light was actually finite, and it was at least 10 times the speed of sound. You're probably already seeing that this was not the most scientific of estimates. However, human reaction times are just too slow. They're around 0.2 seconds, and so it was not possible to tell if the delay from opening lantern A to seeing the light of lantern B is because of the actual speed of light, or just because one person was slightly slow to open their lantern. And many scientists refused to accept this result. So later, the Jovian moon experiment in 1676, and a Jovian moon is a moon of Jupiter, this gave us the first calculated speed of light. So it was done by a Danish astronomer called Olaf Rømer. I don't know if I'm saying that right, but he noticed something about the eclipses of Io. Io is the innermost moon of Jupiter, the moon that's closest to Jupiter, and so Earth obviously orbits the Sun, and also Io, and also Jupiter orbits the Sun, and you can see the blue lines there are the orbit of Earth and a small section of the orbit of Jupiter. In the meantime, Io is orbiting Jupiter, and occasionally Io will go behind Jupiter from the perspective of Earth, and it will pass behind Jupiter and it will come out the other side, and we know how long this should take. But Rømer noticed that when Earth was moving away from Jupiter, the moon stayed behind Io 22 minutes longer than when the Earth was moving towards Jupiter around 6 months later on the other side of the Sun. So why would this happen? Jupiter isn't getting any bigger, it's not getting any wider, and Io isn't slowing down mysteriously while it's back there. So what's happening, at least what Rømer thought, is that light has to travel from Io to Earth. And when Earth is moving away from Jupiter, it has to travel that little bit further, and this takes a little bit longer. On the other side of the Sun, when Earth is moving towards Jupiter, then you get the light meeting Earth on the way. It has to travel slightly less distance to get to Earth because Earth is traveling towards it to meet it. So Rømer suggested that the difference in the eclipse time was due to light having a little bit further or a little bit less far to go to reach us from Io. So with this information, he was able to calculate a value of 2.1 times 10 to the 8 meters per second on light. So this is inaccurate, it is not correct, because he had some incorrect data on some of the distances. But it is in the correct order of magnitude, so you can very much say that this is the first realistic attempt at learning the speed of light. Following that, in 1728, was something called the stellar aberration experiment. So stellar aberration is an effect that causes the position of stars to change because of the Earth's motion around the Sun. This is not something we're going to go into in detail, but a common metaphor is that if you are standing in the rain and there's no wind, the rain will come straight down on your head, and so it will appear to be coming at 90 degrees from the sky. But if you are walking, or maybe running would be better, you will feel the rain on your face, as if the rain is moving down, but also towards you slightly. Of course, it is not. You are moving towards it. But if you were to calculate the angle of the rain, it would be not equal to 90 degrees from your frame of reference moving through it. So there was an English astronomer, James Bradley, who used this effect in an experiment to further get closer to the value of c. And so by knowing a little bit more accurately the speed of the Earth and things like that, he was able to calculate 301,000 kilometers per second by measuring the angle to various stars at different times around the Sun. So when you're taking measurements as the Earth goes around the Sun, this takes quite a long time. It takes 365 days, in fact, to take measurements all the way around the Sun, only once. So it took Bradley 53 years of work and calculation to finally confirm these numbers. And his success convinced all scientists finally that c was a finite value, because some people hadn't been completely convinced by Romer's work earlier. However, Bradley's experiment required him to be able to accurately measure angles of 1/200th of 1 degree. So that's a 200th. Excuse me. But Bradley's experiment worked by being able to accurately measure angles as small as 1/200th of a degree. So take 1 degree and divide it by 200, and that is the sort of angle Bradley had to measure. So you can see why his work was so difficult back in the 1700s. So the cogwheel experiment. Armand Fizeau was a French physicist from a rich family, and he was the first person to calculate c accurately using completely terrestrial equipment, Earth-based equipment. So this is a schematic of his setup, and you will see the idea that came from Galileo's experiment coming back here. If you can create a path that you know the length of, and you can make light travel that path, then you then only have to find a way to measure the time it takes. And if you can make that path longer, then you have a better chance. So this is a very small diagram, but Fizeau's equipment was much longer than this, and he extended the path. What you have is a lantern, and that beams through a piece of glass and then through a cogwheel. There's a blue cogwheel there. Sometimes it will go through and hit the mirror at the far right, and sometimes it will be stopped if it hits one of the cogwheel's teeth. And then sometimes when it hits the mirror and comes back, it will hit a gap and it will pass through and it will be reflected up at 90 degrees into the detector above. But if you make the cogwheel faster or slower, then suddenly it will be cut off. It will not pass through. It will hit one of the teeth. And then if you speed it up or slow it down more, you will find that it will pass through again. And so by calculating the speed change of the cogwheel to get different flashes of light, you will be able to estimate the speed of light. And Fizeau determined the speed of light to be 3.15 times 10 to the 8 meters per second. Another guy called Leon Foucault created another mirror-reflecting experiment, and this was refined by Michelson a few years later. So we're going to skip straight to Michelson's experiment now. And that was the rotating mirror experiment in 1878. So the German-American physicist A. Michelson was one of the great minds of his time. Many scientists get that accolade, but I think Michelson certainly deserved it as much as any. So he improved on Foucault's design. Instead of 60 feet long, this piece of equipment was 2,000 feet long, around 650 meters. And what we have is a light source creating a beam, and that shines on a mirror, is reflected to a far mirror. That shines on a barreled mirror, which is reflected to a far mirror, and then comes back, hits the barrel again, and is reflected down into a detector. But the barrel can rotate, and the light is only reflected to the detector at a certain position. So the apparatus here allows light to be measured over a path that you can measure, and if you can set the speed of the barrel, then you can set the timing of the pulses of light that reach the detector. And so then you can work out how quickly the light got from the barrel, from the light source to the detector along the path that you have measured. So Michelson got a speed of light at 299,792 kilometers per second, just a tiny bit out, and this was the most accurate measurement of C for the next 40 years. But Michelson was not done there. He went on to invent the Michelson interferometer. Now, science is a continuous process, and every person makes their contribution, but the interferometer really provided a leap forward in the possibilities for analyzing radiation. In the end, Michelson's interferometer leads directly to Einstein. If Michelson had not done his experiments, Einstein would not have been able to calculate special relativity. It is not surprising, then, that Michelson won a Nobel Prize for his work. How does the interferometer work, though? Well, very simply, you take monochromatic light, which means light of a single color, and that means you know the wavelength of the light and the frequency of the light. And you can split it, and you can send it down two different paths of different lengths, perhaps. And so when they get to the detector, they might be in different phases. The waves might interfere with each other. So we didn't understand this wave idea of light very well back then, and we don't need to understand it now. But suffice to say, when waves of light interfere, the way they interfere can tell us a lot about what is happening with that light, how many wavelengths are in the path, for example. So this clever arrangement of mirrors allowed light to be sent along a path of up to 11 meters, even though the apparatus is only less than 2 meters across. So you reflect the light back and forward between different mirrors to extend the path length in a relatively small piece of equipment. So again, you can see that the whole analysis of the speed of light has been this idea of making more and more accurate devices and extending the path length as much as you can on each device to get a more convenient calculation. The interferometer, though, is useful for far more than that. So the 1887 Michelson-Morley experiment made use of interferometers, and this is sometimes called the most famous failed experiment in history. Why would we call it that? Well, the reason was the experiment was designed to detect the ether, or rather, it was designed to detect the movement of Earth through the ether. And this was called the ether wind, but it is more like air resistance, really. But the experiment failed to produce any results that showed the existence of the ether. So everyone assumed that ether theory was correct then, so Michelson wrote that the experiment was negative. It was a negative result. It had not worked. They had not proven the ether. However, what they had actually found was the first evidence that clearly showed that there was no such thing as the ether. There was no universal frame of reference. And so once you had abandoned ether theory, it became possible to ask, is physics the same in all different frames of reference? And spoiler alert, it is, and this is one of the underpinning assumptions of relativity, that physics will be the same in a moving frame of reference, the same as it is in a stationary frame of reference, by some measure. So, we're going to skip ahead now to 1983. So, the speed of light was refined further over the years since the Michelson-Morley experiment. Lasers, which were highly focused monochromatic light with highly accurate frequencies, allowed the interferometer to provide even more accurate measurements, and we eventually got the speed of light accurately to a value of 299,792,458 meters per second. So you can see that Michelson was really only a matter of 3 decimal places out with his estimates. And we often, in quick calculations, round this off to 3 times 10 to the 8 meters per second. Eventually, the precision of this measurement made it possible for us to use the speed of light to define an SI unit, and we actually changed the meter to reflect the speed of light. So before 1983, the meter was defined as equal to 1,650,763.73 wavelengths of the orange-red emission line in the electromagnetic spectrum of the krypton-86 atom in a vacuum. So, as you can see, this was a very precise but very, very inconvenient definition for the meter. And I'm not quite sure where it came from myself, but suffice to say, in 1983, the CGPM, which is the General Confidence on Weights and Measures in English, but in French the initials fit, and they changed the definition so that it is now 1 meter is defined as the distance traveled by light in 1 299 millionth 790 no in 1 299,792,000 299,792,458th of 1 second. You can still see the precision there, but this is something that is much more convenient. So it's only based on a single constant, and that constant now is much more convenient to measure these days than the orange-red emission line of the krypton-86 atom in a vacuum. So you would reasonably ask what the point of it all is. Why has so much effort been put into finding a value of C? Well, one reason is that we use C to measure astronomical distance. Tiny inaccuracies could lead to massive errors in the final result. But much more important than that is the fact the speed of light is a universal constant. So once we understand that it is constant, we can build new science around that understanding. Einstein's relativity is just one example of an advancement that could not have been made without the idea of a finite speed of light. Light is also important when we investigate the universe, so when we measure things in the universe like the distance to the stars or even the mass of stars, we use light and the way that light behaves in order to do that. So that's been our little discussion of the discovery of the speed of light. So we haven't obviously covered each experiment in much detail, and at best you would have a general idea of how each experiment works. But one thing that you can say of all the experiments is it becomes easier to measure the speed of light the longer the distance you can measure it over, and the more accurate your recording device is. So even though the Michelson interferometer only has a path of 11 meters, and the distance to Io is obviously many, many millions of kilometers, Michelson was able to get more accurate results because of his precisely engineered devices, where Romer was not able to use such precision and he did not have such good data. So this shows not just the importance of the speed of light, but the importance of constantly improving our technology and our data recording techniques. Thank you very much for listening, and I'll see you next time.